Hey guys, Mr. Longbreak here again. I hope all is well. Today we're going to be talking about velocity time graphs, which is a little bit different than our position time graphs that we worked on earlier this week. So before we get into what a velocity time graph looks like and its differences from a position time graph, first we need to understand the difference between speed and velocity. And these two terms are used interchangeably quite a bit, and sometimes they can be the same, but there is one distinctive difference. And speed is the distance covered in a certain amount of time. And so the formula for speed is going to be distance over time, and its units will be meters per second. That's the base unit. Meter being the unit for distance, second being the unit for time, and it does not include direction because it's the distance covered in a certain amount of time, not the displacement. So on the other hand, displacement covered in a certain amount of time is the definition for velocity. That's the main difference between speed and velocity. Velocity is talking about how the displacement or how much displacement is covered in a certain amount of time. Its formula is the same thing, except it's displacement, not distance, over time. And its units are also meters per second, so very, very similar. And then the key thing here is that velocity does include a direction. So which direction that object is going in. So here's an example of a practice problem, and you will have to know how to solve for speed or velocity. And both of those formulas are right up here. And so this first question says, if a firecracker explodes 3,630 meters away from you, and it took 11 seconds for the sound to reach you, how fast does that sound travel? Okay, so the first thing that we're going to do is we're going to label what our given variables are. And so the first thing is it says 3,630 meters away. That is a distance. So I'm going to label D as 3,630 meters. Then it says it took 11 seconds. That is a unit of time. So T equals 11 seconds. And it says how fast does that sound travel? So we're solving for speed or velocity. Now our formula is speed equals distance over time. So now I'm just going to simply plug in my numbers. Speed is what we're solving for, equals distance, 3,630, divided by time, 11 seconds. And so if I divide 30,630 by 11 seconds, I get 330. And the unit for speed, if I circle it up here, in our definition is meters per second. That's how many meters, 330, you travel in 1 second. So that is the speed of sound. And so my answer is going to be 330 meters per second. So just be comfortable solving problems for speed or velocity, and you're just going to be using these two formulas to do that. Okay, so now we're going to take a look at a position time graph compared to a velocity time graph. And this graph over here on the right side, and I'll point to the one I'm talking about, this graph right here is a velocity time graph. And what I want you to notice is that I labeled numbers here. 0 being in the middle, and then increasing 1, 2, 3 down, and increasing 1, 2, 3 up as well. Those numbers are very important to include or to think about whenever you are dealing with a velocity time graph. And that's because this y-axis is velocity. It's essentially speed compared to the position time graph where that y-axis is position or distance. So very different y-axes, while the x-axis on both is still time. Another big difference is that we have this bottom quadrant and a top quadrant. Compared to the position time graph, we just have one quadrant. And I'll talk about how that factors into our different types of motion. Now, the first thing that I want to talk about is how can we show no motion, meaning something is stopped. How do we show that? Well, on a position time graph, if you remember, that is going to be a straight horizontal line. That horizontal line could be anywhere on that position time graph, but that is going to mean no motion. On a motion map, I just represent no motion by a large dot. So this right here would represent no motion on a motion map. And now on a velocity time graph, it is a straight horizontal line, but on the x-axis, and it has to be on the x-axis. Here, the number will really help you understand why that is. That number means 0. It means 0 for the velocity. And so for something to be stopped or have no motion on a velocity time graph, it has to have 0 meters per second. Otherwise, or in other words, it has to be on that x-axis. So that is a big difference with no motion on a velocity time graph. It has to be on the x-axis versus a position time graph. It could be anywhere. This also means no motion, either the top one or the bottom one. Okay, next let's talk about direction. Meaning, are we going in the positive direction, meaning away from the origin, or are we going in the negative direction, meaning we're going back towards the origin? Well, on a position time graph, the direction of the arrow had everything to do with the direction. So for instance, if I had an arrow going this way, that would be the positive direction. It is going away from the origin. Versus if I had an arrow going in this direction, that would be the negative direction. It's going back towards the origin. With motion diagrams, if you remember, there is no direction. So no matter what I have for a motion diagram, I can't show direction at all. Now, velocity time, direction is shown differently. And anything in this top quadrant here is the positive direction, meaning it's going away from the origin. And anything down here in the bottom quadrant is the negative direction. So for instance, if I had a line like this, that would be the positive direction. If I had a line like this, positive direction. However, if I have a line like this, negative direction. A line like this, still negative direction. It's going towards the origin because it's in that bottom quadrant. A line like this, negative direction. So direction is shown by the quadrant that it's in for velocity time graph versus on a position time graph, it's based on whether it's going towards or away from that origin or x-axis. All right, next we're going to talk about how do we show constant speed. Meaning the object is moving at a specific speed, one speed, throughout a duration of time. On a position time graph, that was shown by a straight diagonal line. Both of those would show constant speed. This would show constant speed. That would show constant speed. If it is a straight diagonal line, that represents constant speed. Okay, on a motion diagram, the dots would have to be evenly spaced. To show a constant speed. Okay, now on a velocity time graph, it is going to look a little bit different. On a velocity time graph, we are going to have a straight horizontal line that is not on the x-axis. So for instance, this would be a constant speed. It is going 2 meters per second throughout a duration of time. Another example of that down here. That is still going 2 meters per second throughout a duration of time. The only difference between that line and the line I drew earlier was this is the negative direction versus this is the positive direction because it is in the top quadrant compared to the bottom quadrant. I'll do just a few more examples. If I had this line, constant speed. If I had this line, constant speed. So any straight horizontal line on a velocity time graph will equal constant speed. And just think about it with the numbers. This is a velocity. This object is moving 3 meters per second throughout a duration of time in the positive direction since it's in the top quadrant. This object is moving 1 meter per second in the negative direction because it's in the bottom quadrant. So that is constant speed. Okay, next let's talk about how do we represent increasing speed. Meaning an object is moving faster and faster and faster throughout a duration of time. Now on a position time graph, our slope needs to go from shallow to steep. Meaning here's one example, shallow and then steeper. That object would be getting faster, it'd be increasing its speed. Another example is shallow, oops, I'll start over on that one. Shallow and then steeper. That object is getting faster over time. It's increasing its speed because the slope is becoming steeper. Now, how you represent that on a motion diagram, if you remember, is our dots gradually get further and further apart. So that's increasing speed with a motion diagram. Well, how about a velocity time graph? How do we show increasing speed? Well, increasing speed is going to be a diagonal line. And it's going to be a diagonal line showing the speed increasing. Here's one example. This particular object is moving 1 meter per second at that time, now 2, and now 3. It's changing its speed or velocity over time. It's increasing its speed from 1 to 2 to 3. Therefore, that would represent increasing speed in the positive direction since it's in the top quadrant. Now, what about this line? This line also shows increasing speed, and a lot of people would say decreasing speed because it's in that bottom quadrant. Well, this is increasing speed because it is going from 1 to 2 to 3 meters per second. It's getting faster over time. The only difference between that line and the line I drew up here was this was the positive direction going away from the origin. This is the negative direction going towards the origin because it's in that bottom quadrant. So that's how you show increasing speed on a velocity time graph. Last type of motion is how do we show or represent decreasing speed? Meaning the object is getting slower and slower and slower over time. Now on a position time graph, instead of going from shallow to steep, we're going to start off steep and become shallower. Meaning our slope is becoming shallower, less steep, therefore it's decreasing its speed. Another example of that would be this, steep to shallow. That particular object is also starting off very quickly, as represented here as the steep slope, and then it's slowing down, representing by that bottom part of the line. So both of those would show decreasing speed. On a motion diagram, we would draw our dots getting closer together. So that would represent decreasing speed with a motion diagram. Opposite pretty much of increasing speed, where the dots are getting further apart, they're getting closer together. Now on a velocity time graph, it's pretty much opposite of what we were just talking about with increasing speed. We're going to show the object going down towards that 0. So here's one example. That would be decreasing speed. And here's another example. Both of those would show decreasing speed. So if I use these numbers to help us out here on the y-axis, this object started off going 3 meters per second, then 2, then 1, and now it's almost 0. So that particular object was decreasing its speed from 3 all the way down to 1. Same thing with down here. This object started off going 3 meters per second, then 2, then 1. It's decreasing its speed. The only difference here, just like our other ones, is this is the positive direction since it's in the top quadrant, and this is the negative direction because it's in the bottom quadrant. Okay, so that wraps up our discussion on velocity time graphs. If you have any questions, please reach out. I hope all is well. I hope you guys are staying safe, and I still miss you guys a ton. All right, we'll see you later.